Hello, and welcome back to Shiksha DaCosta. Today we're going to learn how to solve problems with line segments. In this lesson, you'll learn how to apply line segment analytical geometry to real life to solve problems that involve the slope or the length or the midpoint of a line segment. To start us off, here is an example. When canoeing on a lake, Julianne discovers that she is sinking. Oh no, she's so far from shore. Which of the following points, A, B, C, D, or E, on a nearby beach should she aim for to get to safety the fastest? If you'd like, you can use the link over here, which I'll also put in the description, to test out which of these has the shortest distance to shore. Pause the video here and go ahead and explore that and resume it when you're done. All right, well, hopefully you recognize that probably the shortest one, the path that'll get her to shore in the quickest time is if she aims for point C here. And what did you actually notice about that? Pause the video here and ponder this question. Well, if this is the shoreline, notice it is pretty straight in a line. If I sort of draw a line to represent that shoreline, and I draw a line that represents Julianne's path from where she started sinking to the beach, you might notice that these two lines meet each other at a right angle. And so her path to shore, it should meet it at that right angle, or should be perpendicular to the shoreline if she wants to get there the fastest. So this is a pretty good example of a place there where we might see analytical geometry lead us to some success in real life. In this next investigation, I'd like you to determine if this is a right triangle or not. Pause the video here for as long as it takes you to do that. Well, one thing we can know for sure, even though this kind of looks like a right triangle, there's no guarantees unless we actually prove that this angle is 90 degrees. So one thing I know is that triangle ABC is a right triangle only if there's a 90-degree angle, only if two of the edges are perpendicular to each other. Fortunately, because of what I know about analytical geometry by now, I should be able to figure that out. So then hopefully you were able to as well. One thing you should know by now about perpendicular lines is that if you find out the slope of those lines, they should be in the negative reciprocals of each other. So what does that mean? Well, it means that if I can find out the slope of line A to B, or the slope of line A to C, or B to C, in fact all three of those, I can then compare them to see if two of them are negative reciprocals. So for example, if I was to find the slope of line A to B, I would just use the slope formula, right? I subtract their y values, subtract their x values, and I find out that the slope of this line is 4/3. You can go ahead and pause the video here, and if you weren't able to figure out the slopes of these two lines already, and go ahead and use my example to solve for that. All right, well, the slope from B to C, that's this purple line over here, again, I just use the slope formula, I plug in the y values and the x values, and I get -2. And so that line has a slope of -2. The line from A to C, so that line right there in teal, again, the same slope formula tells me that that slope is 1/2, 1/2. The rise is 1, the run is 2. And in fact, if I notice, these two actually are the negative reciprocals of each other. -2 is the same thing as -2/1. And if I multiply them together, I get -1. And so I believe now I can confirm that AC and BC are perpendicular. And so I'll draw a little square there to indicate that. And this confirmed is a right triangle. So analytical geometry is the branch of math that marries both algebra to geometry. And you can use the formulas that we've learned throughout this unit so far to calculate the length of a line, the midpoint of a line, the slope of a line, to solve problems that involve those geometric diagrams. If it helps, you can always draw a coordinate plane and a graph, and that can help you verify your solution visually, as well as help you solve the problem. Can you find the area of triangle ABC, which has these three vertices? Well, one thing I know about the area of a triangle is it can be found by taking the base times the height and dividing it by 2. Now, it would really help if I could visualize this triangle, so I'll pull up a coordinate grid, and I'll put point A here at 6 and 7, point B at 0 and -3, and point C at -2 and +1. And if I connect those lines, those points with lines, I can see that this is a triangle. It doesn't quite look like a right triangle, but no matter, I still know a triangle's formula is always the same. What makes it really hard for me is I can see, that any one of these sides could be the base, but the height might be pretty difficult to find. Pause the video here and see if you can try and do that by yourself. All right, well, like I said, the height is pretty difficult to find, so don't beat yourself up too much if you are unable to do that by yourself. Let me walk you through it here. So the base and the height, like I mentioned, any of these three sides can be the base. And I'm going to say, for example, this side down here is the base. So I'm going to color that in purple. And now I need the height. And I don't have a red line here to indicate the height here. But I can maybe, if I say that this is the base, if I extend this line just a little bit, then the height should be perpendicular to this. So I could, for example, draw a line from this point going straight down here. And as long as it meets it at a right angle, this line, the length of this line segment, could be considered the height. So what do I have to do? My job is to find out the length of this line segment BC, that's the base, as well as the length of this line segment from A to some point over here, and that's the height. And all I know is that line must be perpendicular to this line. Well, that perpendicularity gives me actually a big clue, a great starting point. And what that starting point is that if I can find out the slope of this line, the slope of line segment BC, which very easy for me to do with the slope formula. I just find the rise divided by the run, and that tells me that it's about -2. That slope right there. I find the y-intercept, and I can see right away that this point right here is already on the y-axis, so the y-intercept must be -3. Then this dashed line, or the line that contains this line segment, is y equals -2x minus 3. That's the slope of the line, and that's the y-intercept of this of the line that goes through this line segment. And that helps me because that tells me that this line here, which contains the height, has to be the negative reciprocal. So if I'm trying to find the equation of that line, I know that the slope must be the negative reciprocal of this. I also, to find the equation of that line, I need not only the slope, but the y-intercept. And in order for me to find the y-intercept, I need one other point on the line. I need an x and I need a y. And I can pretty easily get that from this point that is on the line, that I know for sure is on the line, 6 and 7. So I'll use the y values and the x value from there. I'll plug those in along with the slope, that again is the negative reciprocal of -2, or just 1/2. And I'll start to evaluate. So a half of 6 is 3, and then I'll subtract 3 on both sides to remove the value of 3 on the right, subtract 3 on the left side to keep the equality true, and 7 minus 3 is 4. And that actually is confirmed by the line. I can see it goes through the point here 4, but I don't want to estimate any points ever in analytical geometry. I do want to analyze it, right? So what I found basically is that the equation of this line right here, the line segment that I could use to describe the height, its equation is y equals half times x plus 4. I've got the slope, and now I've got the y-intercept. The reason I've done all of this is because now I can use this line segment here and this line over here to find out this point right here. That I'll label point D, and that's the point of intersection between these two lines. And a point of intersection, the coordinates can be found algebraically quite easily. All we have to do, like you can see here, is take the equations and make them equal to each other and find the value of x that makes that true. Both of these lines are equal to each other at this point. What is the point value of x that makes that happen? It looks like it's about, I want to say like -3. But again, I don't want to estimate when I can just analyze. So I'll just have to solve for x in this equation. I'll add 2x on the right side to get rid of the negative 2x term. And then I have to, of course, do the same thing on the left side. I'll subtract 4 at the same time on the left side to cancel that out. And at the same time, I have to subtract 4 on the right side. And now I've got all my x terms on one side and all my numbers on the other. So 0.5 plus 2 is 2.5. Negative 3 minus 4 is negative 7. I can now get rid of the 2.5 by dividing both sides by 2.5. That's the opposite of multiplication, is division. And then negative 7 divided by 2.5 is negative 2.8. And that's the x-coordinate of point D. In order for me to find the y-coordinate, I can just take the x-coordinate and plug it into either this equation of a line or this one, and I've chosen to use this one. Again, it shouldn't matter. They should both give you the same y-coordinate, which in this case is 2.6. And so now that I have the coordinates of D, I can find out the exact value of the height, and I always had the coordinates of B and C, so I can find the exact length of the base, and then I can multiply those and divide by 2. So to find the base first, that is the line segment B from B to C, and the length of a line segment formula, all I have to do is plug in my values for the x coordinates and the y coordinates, and start to evaluate. So I end up getting 2 squared plus 4 squared, which is 4 plus 16, or 20. And I could try to evaluate this, but I'm actually not going to. I'm just going to leave it as its exact value of the square root of 20. Now that I know the base, I do need to find the height. So I'll use that same line segment formula, right? The length of a line segment from point A to D, subtract their x coordinates and square it, subtract their y coordinates and square it, and add those two squares and square root it all. That'll give me the height. And so that would be 6 minus negative 2.8, 7 minus 2.6. Both of those are as such. We'll square them both and add those two values together to find that the height is exactly the square root of 96.8. So now we have the exact values of the base and the height. We can just plug that into our area of a triangle formula, base times height divided by 2. And if you take all of this and you put it into your calculator, you'll find that the area of this triangle is exactly 22 square units. So there you have it. We found the area of a triangle that has vertices if we are only given the coordinates of those vertices. We were able to find the exact area of the triangle contained within through the help of analytical geometry. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.